back. Chapter 2, Implicit Differentiation, Section 2.6. The functions that we have met so far can be described by expressing one variable explicitly in terms of another variable. For example, you could clearly get y to be square root of x cubed plus 1 or y equals x sine x. Okay? In other words, y is an expression in x. Okay? Some functions, however, are defined implicitly. So here is an explicit description. Here are implicit definitions. X squared plus y squared is 25. That is, you have not solved for y explicitly. X cubed plus y cubed equals 6xy. You have not solved for y explicitly, but there is a relationship between x and y. So how do we, in some cases, it's possible to solve such an equation. You see, look at this. To solve for y, I would move the x squared over and take square roots, which I did. But notice when you take square root, you have positive or negative option. If you take both options, then you don't have a function. You have to make a choice, one or the other, positive or the negative. So you get two functions, right? Because x squared plus y squared is 25 is a circle which does not pass the vertical line test. So it's not a function. If you take the top half, that's a function. You take the bottom half, that's a function. So there are two functions living here, right? One is the positive root, the other is negative root. So y coordinate being negative gives me the lower half. Y coordinate being positive root gives me the upper half. But it is not easy to solve something like this. Something like this, it's not easy to solve. Okay? So a computer algebra system could give you an expression, but the expressions are very complicated. Regardless, this curve is called the folium of Descartes. Implicitly defines y as several functions of x. So for example, from here to here could be one function. Here to here is another function. And then this is the third function. All right. Here, well, they are taking this part as one function, this part as another function, and this part as the third function. So once you say f is a function defined implicitly, we mean this can happen. That is, y is fx. We don't need to solve for an equation of y. So you see, there is something called implicit differentiation. You know how to take derivative here. How do you take derivative here? If you don't know what y is, how can you possibly take derivative? Okay? When you don't know y, and yet you are able to take derivative, the method is implicit differentiation. So the approach is you differentiate both sides of the equation with respect to x, and then solving the resulting equation for y prime. So you may not be able to solve for y, but you will be able to solve for y prime. Okay? So we are assuming in this section that y is implicitly determined. Okay? And then you're going to take implicit differentiation. Okay? So here is an example. X squared plus y squared is 25. Find dy dx. All right. Then find equation of the tangent to the circle at this point. Well, what do? Find dy dx. In other words, apply derivative with respect to x of both sides. Derivative with respect to x of both sides, that is d by dx of both sides. Derivative of this plus derivative of this equals derivative of constant is 0. Now let's look at these two. Derivative of y squared with respect to x. Well, this is where the chain rule shows up. You are going to take 2 down, reduce the power of y by 1, and because y is different from x, you still need to do dy dx. So derivative with respect to x of y squared is 2y dy dx. On the other hand, derivative with respect to x of x squared, look, the variable is same, it's simply 2x, right? Because the variables are different, you need dy dx. That's the chain rule part. You are multiplying by dy dx. All right. Right hand side, if you recall, was 0 because that was a constant. Now you can solve for dy dx. Move the 2x there, get it, negative 2, divide by 2y, and you have negative x over y. Okay. Now the point 3, 4. X is 3, y is 4. So slope at 3, 4 is negative 3/4. Once you have slope and you have the point, you have your equation of the tangent line. All right. Another way of doing this is solve for y. You actually get something plus or minus. 3, 4, both positive, so you are in the upper semicircle. So you are taking the positive root. In other words, your function is square root 25 minus x squared. Take its derivative. It's a bit of a work. And then substitute 3. You get slope. And then you get equation of the tangent line. So either way could be done. But implicit differentiation is by far easier. Okay. So in most of the times though, I must say, you cannot necessarily solve for y. In this case, you could, but not always. Okay. So that completes the lecture slide. Next lectures on, I'll go over problems from web work.